Hi, kids. All right. Second part of our circuit in review video is all about capacitors. Remember, it's called a capacitor because it has the capacity to store charge and energy. Really, all a capacitor is two parallel plates that's separated by an insulator. Okay, so hey, look, here's my two parallel plates. They're separated by an insulator. First thing, make sure you realize, and yes, this is on your formula sheet, that this equation is true. It's valid for a capacitor. This stands for the dielectric constant. That's what you're putting in between, the insulator that you're putting in between the two plates. If most of the time it's air, then this would be 1. This is that constant that's on your formula sheet. This is the area of the plates. And then this is the distance between the plates. It should make sense. If you have a bigger area, you have a bigger capacity to store charge and energy. If the plates are further apart, okay, it's harder to store charge and energy. Remember, if this was connected to a battery, okay, now I'm trying to draw this in 3D. You know, most of the time you would just see it look like this. Okay. Remember, here's how your capacitor works. There's already charge in the wires. There's already charge in the capacitors, but each side starts out neutral. You know, one of these super duper important graphs with capacitors is this graph. So you start out with no charge, so no voltage across. As time progresses, you know, hey, if you remember, like we passed little wiffle balls, but if you know, some charge gets pushed onto here, so this would be positive charge, so positive charge gets pushed on here, it scares a charge off the other side, which then gives us a negative charge. And then another positive charge gets pushed on here, it scares a charge off the other side, giving that a negative charge. It puts another positive charge here, it scares a charge off, and so on. And as this process is going, it is going like this until you get to a point here where for this particular circuit, if you do your loop rule, this voltage and this voltage would have to be the same. Speaking of loop rules, just keep this in mind because this is important with capacitors. Remember, this is the plus, this is the minus of your battery, which means this is going to be the plus, this is going to be the minus of your capacitor. But if I was doing a loop rule, so let's say I start here and I'm going to go around. Well, if you look, I would add the voltage of the battery, and then do you see how I'm going the wrong way? So then I would subtract the voltage of that capacitor, and then I'd end back up at 0. So, but just make sure you think about how the charges are on your capacitor when you're doing a loop rule. This equation, like I said, is super duper important. If you find the slope of this equation, okay, the slope is your capacitance, which most of the time I write C equals Q over V. On your formula sheet, it's written this way. And the reason they write it this way is because the College Board always likes to say this depends on these two variables, where this really depends on this stuff. It depends on your area, your distance, your dielectric constant, all that stuff. But most of the time, I write it this way because I want you to always be thinking about this super duper important graph. In fact, the slope tells you the capacitance. The area underneath, well, if you think about units, it's going to be coulombs. This is joules per coulomb. So if you take joules per coulomb times coulomb, you get joules. So the area underneath tells you the energy that's stored by the capacitor, which would be 1/2 Q times V. Yes, that is on your formula sheet. Or if you were to take and solve this for Q, Q equals C times V, and then you plug that in, you would get this formula, which is 1/2. Actually, the way it's written is delta V, but same difference. C delta V squared again, on the formula sheet, but these two things are really the same thing. Okay, it is super important. Do you understand how a capacitor charges up? Remember that charge gets pushed on here. It pushes off here. If you have a perfectly uncharged capacitor, for the instant you hook up your circuit, it acts like a closed switch. Okay, if you have a completely charged capacitor, then it acts like an open switch because no more charge can move in your circuit. Okay. Last, this formula is on your equation sheet, and I just want to make sure you understand what it represents. Okay. This is the electric field that exists between your capacitor. Really, all this equation is if you remember this equation from our electrostatics. Okay. If you take this equation and you combine this equation and this equation, you end up with this. But if you look on your formula sheet, that is there. Okay, and I just want to make sure that you understand why they put that there. Personally, I don't think they need to, because if you understand this other stuff, you can get it. But it is there just in case you need it. Okay, so that's the basic stuff about capacitors. If, for example, let's say we did this to start. Let's say I had a basic circuit like this. Okay, where I have a capacitor, I have a light bulb here, and you had to describe what happens. And again, it is really important that you understand how this works. At the start, if your capacitor is uncharged, this acts like a closed switch. So essentially, I just have a circuit with a light bulb in it. My light bulb lights up. It lights up bright. Well, over time, the light bulb's going to get dimmer and dimmer as you are building up charge and voltage across there, until finally, when this gets to be the same as this, if you do your loop rule, well, there's no more current, your light bulb turns off, so that this voltage would have to be equal to this voltage. Okay, but again, make sure that it makes sense how it builds up. Let's make sure you're okay with series and parallel rules for capacitors. So if I have a series circuit like this, okay, versus if I have a parallel circuit like this, again, as long as you understand how charge behaves in a circuit, you should understand a lot of different things. But if you look here, remember, charge gets pushed onto this one, onto this side. It scares the charge off, and then it pushes the charge onto here, scares the charge off. Well, that means if whatever charge I'm scaring off the other side is getting put on here, that means the charge for a series, capacitors in series, has to be the same. So the charge for a given circuit is going to be the same. So in this case, QT would equal Q1 would equal Q2. Okay, don't memorize it, understand it. Where here, if you look, charge gets push. When it gets here, well, some of the charge might get pushed this way, some of it might get charged this way, which is why whatever charge comes out of the battery is going to be Q1 plus Q2. Very similar to current, like with resistors. If I add another capacitor in series, okay, this circuit actually has less capacitance than this circuit. Okay, one way you can think of it, if you think about this equation where it's the K, this A over D, do you see with respect to the battery here to here versus here to here? Here I have increased the distance. Those two plates are touching the battery, which means my total capacitance goes down, which is why if you look on the formula sheet, this is the formula that you will see on there. And yes, that is on the formula sheet. Okay, but to find total capacitance in series, you add up the inverses and then you got to flip it. Whereas if I added another capacitor in parallel, okay, that if you look here, if you think about in terms of this equation, do you see how I have, like if you look, I've increased the area touching the battery, which means if my A goes up, my capacitance goes up, which is why in parallel, that's how you find the total capacitance. Okay. Again, this formula would be on your formula sheet. Make sure it makes sense. You are expected to be able to do combo circuits. You know, if I have something like this, you know, where you have to be able to redraw and simplify the circuit. So hopefully that makes sense, you know. Hey, look, I would combine these two by doing this, and then I would have three, I would redraw that. Then I'd have three here in parallel, so I'd simplify those by doing that. And then I could find the total capacitance, total energy, total charge in my circuit by doing it that way. And then the last thing to note, which is really big and important in this unit, is that they have, a lot of times you'll be asked to solve circuits where it has capacitors and resistors in it. So for example, let's say I have a circuit like this. And then it asks about, it will always, for this class, it's always the initial state and then the steady state, which means like after it's been hooked up for a long time. So initially, if you're thinking about this, initially the current would go like this. Okay, it would essentially, you would just have one resistor in your circuit. Why is that? Because the reason why that would be is because this is going to act like a closed switch, so the current would just flow like that. Okay. After a long time, then you would have a circuit that looks like this. Okay. So the initial state, you have one resistor in your circuit, and then the final state is you added two more in parallel to it. But because we did add resistors in to the circuit, your total current would go down. But if you're not sure, make up numbers. You know, if I call this 1 and I call this 1 and I call this 1, you can actually solve it and see. Versus if you had something like this, let's say we had a circuit like this, where you have a capacitor here. Okay. The initial state would be, hey, I have one resistor here, and then I have three resistors in parallel. And then the final state would be, I have a resistor here, and then I have two resistors in parallel. And then just keep in mind, in this particular case, the final current, you know, up here, the final current would be smaller. Why? Because I added these resistors. In this case, my final current would also, let's see, my final current would also be smaller because my total resistance for this part would go up, which means your total current would go down for the whole thing. But again, if you're not sure, make up numbers and solve it. But most importantly, make sure you conceptually understand what the heck is going on. All right, that's that. Bye, kids.